Thank you very much. Good morning or good evening or good day, whichever time zone you are at, because I can see that some of you are quite from far away. Can you hear me properly, Chris, or anyone else?
Yeah, I can hear you fine.
Yeah. Okay. Thank you. So first of all, thank you very much for this opportunity, for the invitation. I really think that this is a great idea to have this online seminar series, and I'm very proud that you and Jaja and Marina are actually doing this, because at some point you were all in Sheffield in the past, and maybe in the future as well. So the topic would be waves and oscillations in the solar atmosphere, but from my perspective. So I'm not going to give maybe a whole coverage of the waves and oscillations, but maybe more from my perspective, or how I see this stuff. And before I would go into the seminar, I also would like to say that thank you for colleagues who helped me during my career to learn about waves and oscillations. Initially, I prepared the page where I started to write the names, but after I realized it will not fit one page, all these folks whose contributions I would use, I said, okay, I will just count the numbers. So I had about 15 PhD students, 55 actually so far, and about 25 postdocs. So I would like to thank all of them, because many of the slides I used or revised from their studies or from their contributions in the past 2 decades. And of course, also I would like to thank the colleagues from whom I learned a lot on these waves and oscillations. I started with Jerry. I don't know whether Jerry Dole was able to join today. And then I moved to St. Andrews with Bernie Roberts, and they were my mentors in the beginning. So I would like to thank all of them. And these days, when I go a little bit into the instrumental side, I do a lot of work with Mihalis and his coworkers, and of course, because of the solar and the Priest aspects, also with Sarah and Hugh from MSSL and from Robertus. So thank you very much to all of you who contributed to this research, what I tried to cover today. So yes, how I see this, so what aspect of the energy wave research I would like to cover today is the following. As far as I can see, there are many big questions in solar physics, but in the wave context, I see here actually 3 big questions. One is that how close we are to solve one of these great problems of astrophysics, which is the heating of plasma. That's, when you these days read a proposal, almost irrespective of what area you are coming from, whether it's an observational, whether it's a theoretical one or a numerical one, you will always see, likely you will see that the proposal is linked in some aspect to the heating of plasma. And then, whether it's IRIS, whether it's SDO, whether it's DKIST, whether it's EST, all these instruments also have on their agenda very high to solve the heating problem. And each time, I think when we write the proposal, we say we will make a breakthrough, and probably we do make a breakthrough, because this is a very long process to understand the coronal heating. And then the next is, well, okay, right, there are many theories to consider plasma heating. It's not just necessarily waves, it could be also in relation to the reconnection processes, or even when you consider the medium not as a continuum, but by particles. There are many theories. But today I would like to go into a little bit of the wave heating aspect. So how close are we to the wave heating aspect? And here, what my experience is in the last, unfortunately, 20 plus years, is that when I started, or it's even 30 years, when I started, I learned at university that there is the sun and there is the atmosphere. Okay, there are sunspots, but the atmosphere is maybe heated kind of globally. That's what I learned. And I remember that we had a lecture on acoustic waves and how they steepen into MHD waves, how they become MHD waves, and how they will heat the kind of global corona. That was about 30 years ago. And what I have seen as we progress with instrumentation resolution, actually we realized that the story is not that simple. The more we have improved resolution, the more we see that there is a lot of inhomogeneity. And my belief today is that all these various, not all of the various inhomogeneities, but many of these inhomogeneities maybe are heated differently. So now I believe that instead of looking for a global heating mechanism, probably we should look for local heating mechanism. And I'm going to talk about that a little bit later. And the third aspect I would like to cover, if time permits, is how one particular aspect of MHD wave research has developed, and that is the solar magnetoseismology, abbreviated as SMS. I believe that because of the wonderful improvement in instrumentation, so that today we have imagers, we see the waveguides, we see the various structures oscillating. Now we can have really very sophisticated questions and can even go into sub-resolution investigations of these structures. So solar magnetoseismology, I believe, is a very nice sub area of the MHD wave research, MHD wave and oscillation research. So what's the problem? Why we don't really progress with the heating issue? Well, the first thing is, in my opinion, is that there are many problems, but maybe one of the big problems is the following. If I now have here an observation, and a general observation, an AI image, say this one here on the left-hand side, we see these coronal loops. And unfortunately, at the moment, we can't measure routinely with appropriate resolution the magnetic field in the corona. We could measure up to some level sometimes the magnetic field, but there is no routine monitoring of the magnetic field in the corona at small scale, not even the chromosphere. And by the way, not monitoring the chromosphere, I'm a little bit personally surprised, because that's the driver, in my opinion, for coronal physics. So somehow not developing the instrumentation for routine monitoring of the lower part of the atmosphere, I think, is a bit of a shortage. But anyway, that's where we are. So we have got this wonderful image here. And if we measure the magnetic field at the surface of the sun, these are these little ISO lines, then we can construct the atmospheric magnetic field. And here comes the difficulty. How do we construct the atmospheric magnetic field? From a mathematical point of view, we measure the magnetic field only at the surface of the sun, but we want to solve even if we forget about dynamics, yes, we just consider a static magnetic field. We have to somehow extrapolate the magnetic field. So in an easier case, we may solve the Laplace equation, but if we have a bit of a more sophisticated approach, then we may solve a kind of Helmholtz equation. And the problem is that we only have boundary conditions at the lower end. Yes. So the problem is ill-posed. And this is demonstrated here by this following picture, that I have got here the outline of the coronal magnetic field, of the upper atmosphere magnetic field. And in the middle, the magnetic field is constructed using potential field extrapolation, while on the right-hand side, the magnetic field is constructed by some nonlinear force-free extrapolation. Which one is right? We don't have routine observational programs that could decide or that could select what is the right approach. And I think this is a problem, because if we don't even know what is our configuration to investigate, then how can we then study, for instance, waves and oscillations present in these configurations? And for instance, how can we work out the heating function? So I think this is a real not easy part of solar physics, and I think we need to work on that. So that is one of our big handicaps. as the story has developed about, I would say, two solar cycles ago, let's use time in terms of solar cycle, 2 full solar cycles ago, a kind of general picture was that we have the surface of the sun, and then we have these nice magnetic flux tubes sticking out. They penetrate into the corona. They actually fill the corona, and the idea was that that was the kind of working model in the 1970s. This working model was a little bit upgraded about half solar cycle, 10 years later. So I'm not talking, when I say solar cycle, I mean the 22 years. So it's a half year solar cycle later, about 10 years later. This picture was upgraded or improved a little bit by considering the presence of both open and closed magnetic fields. So we don't just have these nice open magnetic fields up here, but there is also a lot of closed magnetic field. And the story became a little bit more complicated because it turns out later in the 1990s that this closed magnetic field, even at the very small scale, it changes rapidly. I remember that after the trace observations, the idea was that after about every 14 hours, the very small scale magnetic field is completely rechanged, remapped. So, and I think later on this number, this 14 hours, was even reduced to some shorter time. So the magnetic carpet at the surface of the sun is now really changing. And my understanding is that probably is just a few hours, and you have a complete, a very large replacement. Let's put it this way. So in order to determine what is the building block of the solar atmosphere and study their phenomena, like for instance waves and oscillations, became a little bit messy. Thanks to trace, in the early 2000s, we came up with Bart and Tetar with an idea of maybe the building block of the building block of the atmosphere could be something like this: that we don't just have these closed and open field lines, but we have added also dynamics to the picture. Because as resolution improved, not just temporal resolution, we always spend a lot of time to improve temporal resolution, but these days, finally, we also spend effort on improving the spatial resolution. Now we see a lot of small scale structures. So jets could be added to the building block, or even current sheets could be added to the building block. And I think that is for me a kind of toy model, what you see here on this picture, that could be considered at least in the imagery framework, that could be considered as the kind of building block of the solar atmosphere. And then Sven came with his beautiful draw. It's almost like an art, where he captured in 2D what may be seen in the lower part of the solar atmosphere. I think this is a very well cited picture, very colorful picture as well. And you have a lot of stuff here. And he got quite some high citation on this, obviously. But I would like to also call another picture as this one. This is by Rob Rutten. You see Rob Rutten's image of the essence of the lower part of the solar atmosphere. It may seem a bit simple, it's black and white, but as far as I'm concerned, almost everything what is in this beautiful picture and image or artistic view of the lower part of the solar atmosphere made by Sven is already also in Rob's sketch. Unfortunately, he's not cited that much with this picture, although I think he should be. Because as I said, in my opinion, these two pictures are more or less the same. You have the open fields, the closed fields, you have the fibrous structure, you have the jets, etc., etc. And with a little bit of imagination, you would also have the added wave phenomena. Right. So anyway, what we think today is something like this. It could be the building block of the lower part of the solar atmosphere. It's a very, very rich structure. You have got everything. You have got the granulation, you have the P and G modes, they steepen into waves, they hit all these waveguides there, either as shock waves or maybe not developed into shock waves. Then there is a lot of coupling between these waves. I will go into that later. We have got dynamics, like speakers, short lived speakers and longer, the traditional speakers, etc., etc. So this is a very complex picture. And if you would like to understand how to model this, I think it's not that easy. Because from a mathematical perspective, once I got the working model of the atmosphere, I should understand what are the eigenfunctions and eigenvalues of this system. And then any perturbation should be, in principle, the linear should be the superposition of these eigenfunctions. And I think this is a very, very difficult exercise. Right, so that's what we have on the plate if you do a theoretical approach. And then what do we see? What do we observe? On the left-hand side, we have this beautiful SDO image, and on the right-hand side, we have an SDO image in another line. The right-hand side is the 171, and the left-hand side is the 193. And what we see is that the atmosphere is extremely structured. Yes. And the way I have seen in my career that when we improve the resolution, whether it's spatial or temporal, we always find new structures. And this is amazing. I mean, what is actually the smallest structure we may have as a sort of building block? This is a very difficult question. Of course, it depends on your approach. Because if you have got an MHD approach, there is a lower limit. You cannot go below a certain limit, neither in space nor in time, because otherwise you are violating the MHD approximation. So let me just run these movies one more time. What we see here is an extremely structured and dynamic regime. So it's not just that we have a lot of fine-scale structures, you know, loops, small loops, large loops, etc., etc. Coronal holes like this one is a beautiful example. But these things evolve, and this gives a lot of headache, I think, because if the timescale of the evolution is comparable to the characteristic timescale of the wave present in the system, then I think from a theoretical point of view, we really have a difficult issue to make progress. And that's an area, in my opinion, which is not yet developed, although some initial trials have already been made, either in Sheffield or Richard Mortar in Northumbria is moving a little bit in this direction. And of course, in Belgium, Tom has some nice initial papers in this direction. Here is another example, and I think this has really changed our understanding of, it has given a big boost to waves and oscillation studies. This is a trace image back to actually the last century, I could say, even the last millennium. What we see here is a flare is hitting a loop system, and then the loops are oscillating. When this was published, this has given a massive boost to MHD wave research. Because I remember when I was a postdoc in St. Andrews, and we had the National Astronomy meeting, a senior person in the field, I don't know whether he's here or not, he actually made he made a statement. He said there are no waves in the solar atmosphere. And then this statement was very quickly challenged by these beautiful Soho and Trace images. And obviously, we see a lot of waves and oscillations thanks to these observations. Here, I would like to show you another observation. The previous observation was the transversal motion of the waveguide, and this one will be what we call a sausage motion. There will be some sound quite loud of it, but I would like you to listen to this. So this is here a coronal loop, and what you will see an expansion and contraction. And I would like to show this for one good reason. So there will be some noise here, so please turn down your volume if it is too loud. So I play it again. The reason why I show this is the following. This was a kind of first observation in these wavelengths of sausage oscillations, and we turned the oscillation period into the frequency range of the human ear, and we made this, of course, we made the seismologic study, but we also made a press release. And the nice aspect of this is, and that's why I'm showing this movie, is that we made a press release and we called it Heavenly Music of the Sun. And then it was on YouTube. About 500,000 downloads are there as far as I know. And, you know, there was a lot of press attention. And a couple of months later, I got an email, not an email, I got a letter from the American Bible Association. I was a little bit surprised because I'm not involved in that type of thing so much. And I opened the letter and it was addressed to me. My name was even written without spelling errors. And I opened the letter and the letter says that, dear XYZ, thank you very much that you have given another proof of the Bible. I was really surprised what they are talking about because I wasn't aware of this. And it turned out that the fact that we had the press release on YouTube and also, you know, in all these journals, that Heavenly Music of the Sun, they interpreted this as a sort of additional proof of the Bible. So sometimes you have to be careful how you make your press release of your science. Right. And this is another observation here, a beautiful one. Not easy to see this type of oscillation observations. Not easy to make this type of observations. This is a tornado. At that time, about a good 20 years ago, had a 1 to 1 million chance to make such an observation. And this is a beautiful, if you interpret what you see as wave phenomena, then this is an extremely difficult task, in my opinion. Is also very rich in physics. So this is a solar tornado, basically. Right, and then of course these images came. I'm sorry to show so many images. I decided not to show too much maths this time. What we see here is this massive improvement in resolution. These are the, you know, the images of the lower part of the solar atmosphere. And the nice thing here is that we see this dynamic aspect of the atmosphere. Let me run it again. I'm not so much concerned about this part, the loop part, because that's also interesting. But what is really, in my opinion, a massive improvement is to see these small-scale structures here, the spicules. Now, the spicules, as you may know, is one of these subtle and still not fully understood subject of solar physics. And why are they interesting? They are interesting because if just 1% of the spicular material is able to leave the surface of the sun and is able to leave the atmosphere of the sun, that's then enough to account for the mass flux in solar wind. So there are other aspects why spicules are important, and a lot of research has gone into this direction. From my perspective, the interesting bit is how these spicules are linked to waves and oscillations. And that is, to me, you know, to link the jet phenomena into the wave phenomena and to come up with a unified theory which can describe both waves and jets. That's, my opinion, is a beautiful area of science. Let me just run it one more time. So here we can see this beautiful, plentiful, ubiquitous spicular structure. So that's what I have outlined the big questions. I have outlined to you how theory developed, and now and I have shown to you some observations. And if you decide that I have listened enough, I can't really stay here longer because I may have teaching, etc., etc., I'm also giving you some answers to those big questions. And after that, you don't if you are busy or you are not available, at least you can take away these answers to these big questions, and there's no need to continue. But of course, I will continue with the details. So first of all, in the aspect of solar magnetoseismology, I think the major big improvement was the unveiling the sub-resolution structures, thanks to the MHD waves. So we can now answer questions like, what is the tiny sub-resolution distribution of magnetic field or density, all the diagnostic parameters. We can now make a statement based on wave and oscillation studies, whether a waveguide, like for instance a sunspot or a pore, is it a monolithic or is it a thread-like structure? Of course, if you improve resolution, you will already answer this, but even theory is now there that we are able to make this type of answers, whether we have monolithic or whether we have a thread-like structure. Then I think what is interesting, by studying the waves and oscillations, we can also, I'm listing now here a couple of answers to this question, to the SMS question. We can also have now information by looking at the waves and oscillations and using the SMS diagnostics. What is the density, temperature, or magnetic field distribution along the waveguide? Yes, it wasn't that easy to, it's not that easy to determine, for instance, what is the density scale height? What is the temperature scale height? Is there a temperature scale height? There was this huge debate. I remember there was a huge debate between, say, Marcus Ashwand and Jonas Schmerz, how the temperature distribution, and of course many other people follow this up, but I think they were the ones who have driven these these studies. What is the temperature distribution? What is the density distribution along the waveguides? And these days we can answer these questions thanks to the MHD seismology. And of course, the most interesting part is, if you apply MHD seismology locally, what is the magnetic structuring? Because magnetic structuring doesn't have to be the same as density or temperature structuring. Right. And I think the next big step was when the radial structuring, across the waveguide. So once you have got a waveguide, like a flux tube or a slab, a vertical flux tube or a vertical slab, then the real progress, in my opinion, thanks to this SMS approach, was to determine what could happen, or what is the stratification or distribution of density along the radius, across the waveguide, across the slab. But these were still kind of traditional answers. The questions were hanging there for about 20 years, and we made this wonderful progress, but they were still along the same lines. But I think where the new stuff, the real new stuff came, as I have mentioned, is the time dependence. So when resolution was that good, or is already that good, that we could measure so high frequency waves that the wave frequency was comparable to the characteristic changes or lifetime of the waveguide. And that is, I think, a very, very new topic. And another new topic is questioning the boundaries of the MHD approximation, because I think most of the studies of the wave and oscillation studies, they are still in the MHD framework. We hardly go out of the MHD framework. Oh, I see that I made a mistake here, a typo. It should be neutral. And we don't consider, for instance, ion neutral effects. This has been already started. So this is a kind of what I call is the known unknown. We know that we don't know the answer, but we know that we don't know the answer. So this is an interesting. Sorry?
30 minutes.
Already?
Yeah.
This is still introduction. When do we stop? We stop usually at 45 minutes, right?
45 or 50, yeah.
Yeah, okay. Chris, would you tell me when we are at 45, please?
Yeah, no problem.
Thank you. And then of course, there is the so-called unknown so this is the known unknown, and this is the unknown unknown. We don't even know what we don't know. And I think resolution, again, we have now Dayquist, and resolution will actually kick in. I think that the unification of the jet and wave theory is probably an unknown. This is the area that we don't even know what we are looking for. In terms of heating, I think the big surprise is the following. As I said, for a long time, the assumption was that we have these global heating mechanisms. I don't think is the case. For instance, in a magnetic bright point, at the moment, it looks like that alpha waves seem to be a favored entity to heat magnetic bright points. Pores seem to be heated by sausage waves. Motors or spicules, they support sausage and kink waves. Magnetic fibrils, they support kink and sausage waves. When I emphasize, that the list here, whether it's sausage or kink, means that what is found more abundant. Pores seem to be supporting the m equal to 1 alpha wave. This is not to be mistaken by the kink wave, the m equal to 1 kink wave. And then, of course, there is now evidence of the generation of jets by waves and even heating caused by these generations. Then again, the known unknown, the role of partial ionization, how this is in heating. My understanding is, and if there is someone who works in this area, please update me. I don't think that the partial ionization is that, or the ion neutral coupling is that important in terms of heating. I think that story will not go down on history as a big development, but I may be wrong with this. And then, of course, we have the big unknown stuff, what we don't even know in terms of heating. So I just want to leave this here to have an open question. So these were the answers to the big questions. And let's now have a quick review and see how theory has progressed. And once we apply this theory, how we can have some nice new results. So first, very briefly, I just want to make a kind of declaration of how we see the waves and oscillations in structures. It's a very brief review. And after that, we will make applications, and I will stop when Chris will tell me that time is up. So the story started with, the story started probably in the 1960s by Parker and maybe even earlier, but in the way how we now use the framework of the MHD wave and oscillation studies, the MHD framework study was summarized by Bernie Roberts and his co-workers, Pat Edwin's papers in the early 1980s. The fundamental progress was that we have the description of the so-called sausage waves. This is here a slab in slab geometry. And this is the sausage wave, which is symmetric with respect to the axis. And then here is the kink wave, which is actually displacing the axis. Yes, these were the kind of theoretical, and then he gave a full mathematical description. Then also in a follow-up paper, the same people have devised actually the framework for MHD waves in cylindrical geometry. On the right-hand side, you see the sausage waves, and on the left-hand side, you see the kink waves. By the way, all these movies are available at our website. Yeah. Then the next step was, in my opinion, and we had to wait for about 20 years, and I think it is a progress. At least I would like to think it's a progress. When we also consider the twist, you could argue why twist is more important than many other morphological structure. Like expansion of the tube or curvature, etc., etc. Well, it all turns out that most of these structures are second order, while the twist has a fundamental change in the wave characteristics. So we had a paper with my ex-postdoc and a series of papers on this, and we developed the theory for that. Then these days, I'm really into even further developing this wave theory concept by considering that there is asymmetry. So on the left hand, this is a waveguide here, and on the left hand side, we may have different environment than on the right hand side. On the left picture, I show here kink oscillation, and on the right, I show here sausage oscillation. And a bunch of wonderful PhD students, Matthew, Daria, Noemi, and more recently Joe also started to work in this area. Here I just would like to point out the following. If you have got an asymmetric waveguide, even these very simple waves, like for instance the kink wave on the left, may have different amplitudes on the left or on the right hand side. And this is diagnostic information. Because of this information, you can get an additional constraint on all these theories of constructing magnetic field, constructing the waveguide, whether it's a flux tube or a slab or an active region, etc., etc. So that's one of the real powerful tool of SMS, that once you are able to observationally measure the difference in amplitudes, and of course there are other quantities, that you can really have an additional constraint on all these theories. This is here just a very crowded slide, and on purpose it is. We just want to show that how many applications the asymmetric waveguide theory can be made. You know, sunspots, light bridges, jet structures, pores, prominences, etc., etc. So I don't want to go into the detail. This is, as I said, a very crowded picture. I just wanted to highlight the importance of asymmetric waveguides. So I have covered a little bit the magnetoacoustic waves, but I would like to also cover a little bit one of the waves which has got a lot of controversy, and that's the Alfvén wave. So I'm showing now here to you the Alfvén wave in a cylindrical uniform waveguide. In principle, in a cylindrical uniform waveguide, an Alfvén wave would be on an isomagnetic surface. Okay, so even if this waveguide would be structured radially, one Alfvén wave will exist on one circle. Another Alfvén wave with another frequency will exist on another circle. Yes, so this is the property of the Alfvén waves. These are local waves. They are not global oscillations of the system, but they are local oscillations of the system. Meanwhile, the previous examples like the kink, sausage, etc., these type of waves are global oscillations. So when you study Alfvén waves, you will have information about, you will have local information about the plasma in a waveguide. But there is an interesting thing that, you know, let me just run this movie here. That's what you have seen before. But there is also, you can construct isosurfaces in many different ways. So for instance, I construct here an isosurface, and let me run these two movies, where the oscillations are in antiphase in these two halves, right? So this goes clockwise, this goes counterclockwise. Or another possibility is that the waves on the left-hand side of the flux tube are on isosurfaces which go counterclockwise, and on the right-hand side also counterclockwise. So what you see here is this is the normal m equal to 0 Alfvén wave, but these waves are the so-called m equal to 1 Alfvén waves, or plus or minus 1 Alfvén waves. And of course, you could have also the m equal to +2, -2, etc., etc. So the Alfvén waves could also have a very rich structure. And we are just at the beginning to understand that how this knowledge could be used in MHD wave theory, whether it's seismology or heating, how to exploit the observation of these observations, how to exploit the observation of these waves and gain diagnostic information. I think I skipped this, right? I think I skipped this as well. And I come to the case studies. So I have now outlined very briefly what are the big questions from the context of heating and from the context of seismology. I have shown a little bit of how theory developed. Of course, I have neglected many interesting subjects like nonlinearity, etc., wave-particle interaction. I'm not talking about those at all. And now I would like to make some applications or kind of case studies. So one case study would be the observation of torsional the m equal to 1 torsional Alfvén wave in the sun. And this is a paper here, which I hope eventually will be coming out very quickly. Although I have to say that we have probably like a 3-year fight with various referees. not a fight, argument, let's put it this way, a 3-year argument, but I think now we are tending to a closure on this. So what you see here is an observational evidence in a magnetic pore that these m equal to 1 alpha waves indeed exist. And I think this is really interesting because we believe that as resolution will improve by decast, we will have many of these examples. And of course, if the waves are in antiphase, then there will be a huge gradient across the 2 half circles, and that then has heating consequences, etc., etc. So what you see here is observations at 2 heights, photospheric heights, and a little bit further up. And this is how we see that this m equal to 1 torsional alpha waves propagate into the upper atmosphere. Chris, may I ask you, how am I doing if you are here?
Yeah, it's about 40 minutes, just over.
Okay, so I have still about 10 maximum, yes?
Yeah.
Okay, thank you. So what has been done in this paper, you see a top view now, and we have identified the isosurfaces, and then we see the oscillations in these isosurfaces at 2 various heights. And this coincides well with the theory developed in the early 80s. So this is for the m equal to 1 torsional alpha wave. Another nice, well, at least for me, nice study is the oscillations of light bridges. We are still in the framework of a sort of magnetic pore or a magnetic sunspot or a sunspot. And here we have got the light. Here we have got the light bridge, and you see this light bridge is actually a wall. So it's even called a light wall, and I don't go into the details of why, but if this wall is excited, you will see oscillatory motion at the top. Let me just move away the cursor. Yes. So if I now would put a slit vertically here, I would be able to pick up these oscillations. Now, this is thanks to some wonderful, very high resolution oscillations by Iris, and also SDO was supporting. Right, so here is the static image. That's the sunspot. Here is the sunspot. Here are the various wavelengths, AI wavelength, Iris wavelengths. This is here the light wall. And maybe let's focus on this image here. So we have put a slit here on the light wall. And then you see that how the height of the light wall is behaving as function of time. It's a beautiful oscillatory phenomena, and by analyzing this oscillatory phenomena, we can get diagnostic information about the light wall itself. That's one application, and we call it light bridge oscillations. Then I show you another one, magnetic bright points. Magnetic bright points, I like the magnetic bright points because they are small, they are compact, they are almost like an ideal flux tube. And obviously these bright points are kicked by the granulation, driven by the P mode, the vertical motion of the atmosphere, etc., etc. So they ought to show MHD waves. And this indeed is the case. And one particular wave was identified at the end of the last decade, and that's the Alphen wave. By looking at the widths, spectral widths, temporal evolution of the spectral widths of the H alpha line, actually we have constructed the bright point, and we have shown that there are alpha waves present, torsional alpha waves present in this structure. And of course, the question is how many of these things are there? Is it only in bright points, or is it also in smaller structures? Because if it is present in smaller structures, then of course the energetic contribution could be very relevant. This is still an open question. Here is the modeling. If you decide to model this physics, that we have got a driver at the foot point at the surface of the sun. We plug in this driver at the surface of the sun. We have an equilibrium flux tube, and we drive this system. Then what we find is that with a driver, with this rotational driver, we can excite not just the Alphen waves, what we have seen before, but we can also excite the sausage wave. We can also excite the kink oscillation. So the whole expected MHD spectrum is there. And this was very nice because, you know, from a theoretical point of view, this is what we expect. And from the observational point of view, I don't know any papers which actually show that at the same time you have got the kink oscillation, the sausage oscillation, and also the Alfvén oscillation in a waveguide system. Theory says they all should be there. And then the question is, of course, how energy is distributed between these various waves, which one make it what height to what height, and how this energy is dissipated. Then another study of magnetic pores. Let me just show an example. This is here again a beautiful pore, not much internal structure, at least not at that resolution. And the key point of this study was to show. Let me just go to the result part. Yeah. So this study actually has proven the following. You know, once you have got an MHD waveguide, then we usually assume that the waves are evanescent as you go away from the waveguide. So the amplitudes are decaying. We are not studying the so-called leaky waves where energy is actually carried away with the wave. So then inside the waveguide, we have two scenarios. Either the waveguide inside is evanescent, or the waveguide could be also inside having a spatial structure. So if the waveguide is inside evanescent, then most of the perturbation is at the boundary, as on the right-hand side you can see on this picture. Or if the waveguide if the wave inside the perturbation is not evanescent, then another possibility is, this is the so-called body wave, that you have a lot of perturbation at the center or at some other points in the waveguide. These are the body waves. Theoretically, this was derived even as early as the 1980s. But observationally, to prove this, that the MHD operator, you know, in Hilbert space, the MHD operator indeed has this property. So we know that we have the slow waves, we know that we have the fast waves, we know that we have the Alfvén waves. We also know the spatial distribution, you know, sausage, kink, floating, etc. But the question is this property really there, that inside we can have these body waves or surface waves? That's a big question. And that was an open question until a couple of years ago, or 2 years ago, when it was observationally shown in a waveguide in a number of pores, that at the boundaries we have a lot of energy in the system. And here are a couple of examples, 1, 2, 3 examples for surface waves, while on the right hand side you see pores when there's a lot of energy inside. So as far as I'm concerned, this is the paper which was missing for many years, because finally this paper has proven that the MHD operator is indeed as we think it is. And I really mind that this paper was not accepted in a higher profile journal than only in Astrophysical Journal, because I think it would have deserved, you know, the message of it is a very important one. You know, the complete, in order to prove the complete spectral structure of the MHD operator, I think it's a nice result. It's a nice. The idea itself was very nice, and I think to prove that the operator is a complete one, I think it's a nice result. And an interesting finding here was that the sausage waves contain much more energy than actually the body wave. The surface waves. The surface waves contain much more energy than the body waves. That was an interesting result as far as I'm concerned. Chris, where am I now? Maybe at 45?
Yeah, it's actually about 1 or 2 minutes left.
1 or 2 minutes left. Then I'm going to go to the last bit. Yes. I would like to go to this bit. Yes. So now I have outlined to you all the existence of, you know, the story of how the MHD, briefly outlined from my perspective, how the story of waves and oscillations developed in the context of seismology and heating. But one more thing came in very recently, and that is the swirls. So what we see now, there are swirls almost everywhere in the sun. Yes, well, we know that there are swirls everywhere in the universe because spiral arms are swirling. We know that the jets are swirling. We know that water in the bathtub is swirling. So in nature, swirling is a very natural motion. Then the question is how swirls exist in the atmosphere of the sun. And Jaja and Chris and some other colleagues in my group has developed a wonderful tool to actually track these swirls. And I'm not going to go into the details, just outline here the method. So they have developed a method to track swirls at one height in the sun. And of course, you can apply this method also at various heights and even investigate how these swirls actually propagate upwards in the solar atmosphere. And the finding is amazing, in my opinion. So what you see here is SOT data with some resolution. Pixel size 40 kilometer, cadence is about 7 seconds. What we see is in a field of view of say 20 megameter times about 40 megameter, many swirls. All these black and white, not black and white, sorry, red and blue little things popping up, these are the swirls during the time they exist. So plenty of swirls have been found actually in the solar photosphere in SOT images. Then this tool was used to how to go further. Yes. So just to give you an example, it was found about 30,000 swirls that was the estimate that about 30,000 swirls were found. Average lifetime was about 20 seconds, and the total number of swirls was about 1.5 times 10 to the 5 in the photosphere. Yes, with an average radius of a few hundred kilometers. And interestingly, the swirls were located very close to intergranular lanes. Then this study was repeated with SST data, and to our surprise, less swirls were found, but then we realized that this was because of the resolution. So then the conclusion was that it is extremely important to consider the resolution, because resolution will limit the number of swirls you may find in the surface of the sun. So that was one important contribution.
That's 50 minutes, Robertus.
Yeah, I am now closing then. And then we thank you, Chris. And then we carried out some chromospheric observations, and we found that many of the swirls actually do make it into the chromosphere. And then we build up this picture that so there are at least about almost 1.6 times 10 to the 5 number of swirls. How many of them actually make it into the chromosphere? This is a big question. We found that more swirls are actually present in the chromosphere, and that is very important because swirls have a large number of, large amount of energy in themselves. Then the question came, since they are close to the intergranular lane, and that's exactly where the jets are developing. What's the relationship between the swirls and the jets? We call it sometimes tornadoes. That's a very interesting question, and an ongoing research is still there. I can't say more on that. And finally, of course, the big question to investigate is that what is the role of the swirls in the momentum and energy transfer? And we believe now, this is still an open question, but all recent research points into this direction, that we believe that the swirls play a fundamental role in the transport of energy and momentum in the atmosphere of the sun, much more probably than anything else. That's the closure statement. I would like to stop here. Thank you very much.